Hello class, this is a video tutorial on the applications of calculus. In this video we'll be doing one example of optimization. Questions involving optimization work to calculate a numeric value that gives the maximum or minimum volume, area, fuel consumption, profits, costs, or whatever it might be in the question. Since these problems are so varied, no single method can be applied. However, the following steps can assist in solving the problem. Draw diagrams, including all known measurements and variables. Write all formula and equations relevant to the problem. And apply the principles and methods that we already know for calculus to determine maxima or minima. So let's get straight to it. An open box is to be made by cutting the corners from a 60 by 60 cardboard sheet. So let's draw out that 60 by 60 cardboard sheet. It'll look something like this. So this is 60 centimeters, and so is this one here. Let's draw in those the squares in the corners. So that'll look something. So here's my first square. Let's add these in to each of the corners here. There we go. Now for the lengths of these squares, we actually don't know what they are. So let's just let them equal some variable at the moment, x. Let's fill in what we can see from this diagram. Now let's include also the lengths of, the new lengths that we have. This length here, if we consider it, is actually this entire length minus 2 lots of x. So it's 60 take away 2x. That's also the same for this side here. And actually all around this square here. So now, can you imagine if we fold these sides up? We would get so we're going to fold it. We're going to get a cardboard box that will look something along the lines of the following. There we are. Where this base here is actually this side here. And the height of this box, because we folded it up, is going to be the lengths of the squares that we cut out. So that's actually going to be x. Now let's write an expression for the volume of this box. So its volume is going to be the area times height. But we know the area to be 60 minus 2x times 60 minus 2x. So this is going to be 60 minus 2x squared times the height, which is x. Simplifying this, we get x 60 minus 2x all squared. From here, we're going to differentiate with terms of x. So v prime is equal to, going to use the product rule, so it's going to be the first x times the derivative of the second, 2 60 minus 2x times negative 2 plus the second times the derivative of the first, which is x. Simplifying this, we get negative 4x plus 60 minus 2x squared. I'm going to simplify this further by factoring these two groups out. So that's going to be 60 minus 2x outside negative 4x plus 60 minus 2x. Simplifying further, we get 60 minus 6x. And that's what we're left with. So that is the derivative of the volume. Now to find any maximum or minimum points, we're going to find stationary points first. So we're going to let this equal to 0 and solve for x. So we get 60 minus 2x equaling 0. Negative 2x equals negative 60. X equals 30. That is a stationary point, but we don't know whether that's a maximum or a minimum. So let's solve for the next one as well. We get negative 6x equals negative 60. X equals positive 10. So now we have two possible solutions. So now let's determine the nature of both. You can do this in any way that you like. I would like to use a derivative table. So my x values are going to be 9, 10, 20, 30, and 31. The reason for this is I have my critical points at 10 and 30, and I'm just picking values above and below them and in between. Oops. So let's test these values out into our expression here. So let's, actually before I continue, we already know that there are stationary points at 10 and 30. So the derivatives of these points are going to be 0. Those are stationary points. That's what the tangent will look like at those points. Let's substitute 9 into our derivative. 60, I'm reading from here. Take away 2 times 9 times 60, take away 6 times 9. That's giving me 252. That's positive. So that is increasing. Let's substitute 20 into our expression. So it's going to be 60 take away 2 times 20. 60 take away 6 times 20. That's negative 1,200. That's negative. That means this is decreasing. We already have enough information to see that this point here is going to be a maximum because we can see that it's increasing, stationary, and then decreasing. This is a maximum point. So at x equals 10, that is a maximum. So now that we have this, let's find everything that we need to know. So let's find the actual volume of this. So the volume at 10 is equal to, substituting into this expression here, that expression there, it's going to be 60 take away 2 times 10 squared times 10. Substituting this into our calculator, we get 60 minus 2 times 10 squared times 10. That's 16,000. This was initially in centimeters, so this is going to be in centimeter cubed. So the maximum the maximum volume, max volume, is going to be 16,000 centimeter cube at a square length of 10 centimeters. So I hope that gave you an insight into the optimization of problems using calculus. Hope to see you in the next 2 examples. Best of luck.